Hi, this is Andres here reporting on Lab 9. The problem of this lab was to model the motion of a spring mass system using the momentum and energy principles and comparing it to observed data. And my result was that the model is a successful prediction and it satisfies the energy principle. Here was the video given on tracker of Dr. Greco with a spring mass system. The equilibrium length was given as 0.7 meters and the origin I chose as the fixed attachment point, and I chose the spring to move here along in this negative y direction here. I modeled the motion on Python given the mass of the ball as 0.402, the initial position as shown on tracker, and I also loaded this data from tracker here to compare it to the model. I have the gravitational constant, the spring constant. I got the spring constant from the period of the y oscillations. I just rearranged the formula so that the spring constant would be given by this, and I found it to be 6.878, and I found L naught by using the equation. At equilibrium, the mass is static and thus F net is 0, which is the sum of the force due to the spring and due to gravity. Rearranging it, I get this equation where L is equal to 0.7 meters again, and I find an L naught of 0.1266. Here are some energy calculations. The potential energy due to gravity is the mass times g times the height. The kinetic energy is half times the mass times the velocity squared. L hat, the stretch, which is the difference between L and L naught, and of course the potential energy due to the spring, which is half times the spring constant times the stretch squared. I chose delta t to be small and an integer multiple of the frame rate. The video lasted roughly 9 seconds. So here is just using the momentum principle. I have the force due to gravity. I'm updating again L hat, the stretch, and the force due to the spring, which is negative k times the stretch times L hat. Updating F net, updating the ball's velocity using the initial velocity, F net delta t in mass, updating the position using this velocity. Again, this is just using the momentum principle. I'm updating the energy here. I found the change in kinetic energy, the change in the potential energy due to gravity, and the change in the potential energy due to the spring. And since I chose the system to be the Earth, the mass, and the spring, I have the change in energy equal to these three changes of energy, UG, KE, and US. The plot is going to show the ball's position in the y direction, strictly y direction. The red line will show the model. The green line will show the experiment. The blue ball here is the experiment. The orange is the model. Here you have the graph shown, and you can see there is pretty good agreement. As the time progresses, however, the green starts to dissipate in its amplitude, and that is obviously due to frictional forces and air resistance and such. I repeated this entire process for the x oscillations. Again, this is using the x direction now as opposed to the y direction. And I found my model and experiment to be in relatively good agreement. However, it's more off than the y oscillations. I also measured the period of oscillation compared it to the period of oscillation with the y direction, and I found them to be different. This can be explained by the fact that in the x direction it's more of a pendulum style of movement rather than an actual spring movement, and a pendulum's oscillation is dependent on different factors. This would also explain why there is less agreement in the x direction, because I modeled it using spring factors. With this new system that includes the spring, I plotted the change in energy, delta E, by summing up all the changes of the individual energies of the system. According to the energy principle, this is equal to the work done by the surroundings. So we're going to see exactly what that is. As you can see by this red line, the answer is 0, and this makes sense because I chose the system to encompass everything, and there is not really any work done by anything outside of the system. So the energy principle is indeed satisfied, as the work is 0, as is the change in energy of the system. Lastly, what if I had chosen the origin of the system to be at the equilibrium point? Well, then I would just have to shift this spring dot pos up to 0.7, as well as the initial position of the ball, and consequently the spring constant and the L naught would be the exact same, because although these oscillations would all be shifted, the period would be the same in both cases. And if we run this plotting the energies, we can see that the energy plot is unaffected other from the simple shift. So no, the answer is no, it does not affect the physics of the system. Thank you.